I noticed voter registration forms up here. I hope all of you are registered. Any questions to start? Yeah. Sorry? Oh, the modulus is just the name of the amplitude. Right, so C is a complex number. I'm not sure if I used this language in class, but that's the modulus. The modulus is this thing. A squared plus b squared alone equals, I call that the modulus squared, and you call that the modulus. It's the real amplitude of a complex number. Okay? Anything else? All right. So we were working out particle in a box, and we separated variables, and we found, didn't find the white chalk yet. Yeah, here we go. We found, remember we said that our full wave function, whoa, it's bad chalk. Come on, there you go. Our full wave function, there you go, psi of x and t, sorry, and I want to do capital psi, was psi of x, phi of t, and we found that phi of t was some initial phi e to the, well, I could write it two ways, I e over h bar t, or phi 0 e to the I omega t. And there's a minus sign there. There's a minus sign there. Okay? And then I argued this part, this time-dependent part, right? If I look at the, if I ask the expectation, if I ask what's the probability, then this thing times its complex conjugate is just this constant number. There's no change in time. Let me comment on that a little bit. The fact that the time dependence kind of goes away. You can have time dependence in quantum mechanics. I mean, it would be a pretty poor theory, right, if it didn't describe things changing with time. But many problems have no time dependence, okay? And the problems we're going to study have no time dependence. That's not to say there is no time dependence, and there's a method for doing that. And when you take quantum mechanics later on as a junior or senior, I think it's junior, you'll see that. But at this level, there is no time dependence, because anything I ask about the probabilities, it goes away. And we're going to get to the hydrogen atom in a little while, but just a little side note, and I'll mention it now because it's in your book in the reading you should have done up to this point. They mentioned that, you know, the view of an atom is that there's these orbits, right? You know, the old Bohr model, right? And the electron is sort of orbiting the center of the nucleus, the center of the atom, the nucleus. And if I just take a simple hydrogen atom, there's one electron racing around a proton. Advanced electricity and magnetism, this may have been mentioned to you, although I don't think you treated it mathematically. If a charge accelerates, it emits light. Is that a completely new fact to you, or did you know that? You don't know if you did or did not know that. I assume it's a new fact to you. And you'll treat that like in your junior or senior class, right? How that happens. It's fairly mathematical. But if a charge accelerates, it emits light. If it just moves in a straight line with no acceleration, no light. This electron orbiting emits light. So when people first developed this sort of you know, center nucleus electrons orbiting view of an atom before quantum mechanics, there was a big puzzle. Why doesn't the electron just emit light and spiral in, right? We're orbiting the sun, everything's nice and hunky-dory. If we had some loss term, if we were spitting off, well, we are spitting off a little bit of light, but if we were spitting off significant amounts of energy somehow, then we would spiral into the sun and burn up, right? Why doesn't that happen here? And there's a couple of ways of answering it, but one sort of fakey way, and it's not really fakey, is that we're going to solve the Schrodinger's equation for this system, and we're going to come up with a state, and its time dependence is going to be exactly this, and it goes away. And so sort of by the construction of the quantum mechanical treatment, the physical state, the psi of x part, just is stationary in time. It doesn't change with time. It's not very satisfactory maybe at some level, but it's not completely untrue. That is, in a way, why the thing is stable. In this new weird topsy-turvy quantum mechanical world, that's what the thing does. It's just in a state that has no change with time. Now, having drawn this, actually take that exact atom, I do want to mention, also again, because it's in the book, and I think it's worthwhile mentioning now, in the real world, of course, things do change with time. And really the way things will change with time, in quantum mechanics, typically what we'll talk about is there are two states, say, and occasionally the particle will change from being in one state to being in another state. And ignore that over there, because that's not, well, I need to write more than that to describe it. I just want to talk in qualitative terms and bring it back to this notion of the Heisenberg uncertainty principle. If I have an electron, if this electron gets kicked out to this outer state in an energy diagram, and again, this was in the reading you should have done about the Bohr atom. If it gets excited, if this is the ground state and you kick the electron up to a higher state, it can de-excite by emitting a photon. You probably know that. Okay? That's just one of the fundamental ways we get light. That's what's going on in, certainly going on in fluorescent lamps. Okay? And I won't describe how we calculate that, but I did say that there was the Heisenberg uncertainty principle as applied to energy and time. And let me mention that it applies here too, in the following way. If I excite something, and this is generic throughout all sorts of quantum mechanical processes, if I excite something to a state where it lives for a while, and then it jumps to another state, a lower energy state, and that's kind of a very fundamental quantum mechanical behavior. Typically what I'll do is I'll think of that taking on average sometime tau, a decay time. That's the average time for something to jump from a higher state to a lower state, to decay. But also this is how you think of radioactivity. And sort of the probability that this is the probability that the atom takes some time to decay. It's given by an exponential behavior, e to the minus t over tau. And the average of that is tau. So, okay. And in an atomic system, in atoms, tau is typically 10 to the minus 8 seconds. Okay? And the Heisenberg uncertainty principle says something interesting. You know, I think you know, I assume you learned this at some point along the road, that when you have an atom with these orbits and an electron jumps from one orbit to another, it emits light of a certain frequency, right? So the energy between the orbits, this gives me an energy, and then that translates, just as Einstein talked about, into the energy of the, or Planck postulated, into the energy of the photon. Energy equals h bar omega. And omega, of course, is 2 pi times the frequency. So, you know, once you've got the energy between these two orbits, you know the frequency of the light. Okay? But what really happens, if I plot the probability that I get some energy versus the energy, this could be E0 equals h bar omega, where omega was this energy. But in fact, I don't get only that energy. I get sort of a some sort of Gaussian-looking thing. Mathematically, it's something called a Lorentzian distribution, not a bit Gaussian, but it's similar. Okay? It looks the same anyway. Kind of sharper. Doesn't have real big tails. And you can talk about the standard deviation here, delta E, or you call it sigma E if you want. Okay? And it turns out these things are related just by the Heisenberg uncertainty principle. In other words, delta E is going to be h bar. I'm going to throw away factors of 2 over tau. It's a little different. See, tau was not, well, it's also, you can think of it as delta t. Basically, oops, and I didn't write this, this is time. I'm going to live for some time, and I'm most likely to kick off right at the beginning, but I may last a while longer. And these are sort of how often I'll last a certain length before I decay. And so then the average is tau. And it turns out the version of the Heisenberg uncertainty principle here is to say that delta E is h bar over tau, just identifying delta t as tau. All right? And why do I tell you all this? Well, it has actually some physical importance. How narrow is the line? If I actually plug in numbers for tau being 10 to the minus 8 seconds, well, let me do it this way. Let me divide by energy, so I say as a fraction. This is 10 to the minus 8 or so, delta E over E. And I invite you to just plug in the numbers yourself if you care to. This is pretty precise. There aren't many things in your life that you would encounter that are that precise, that are a physical thing. In other words, there's a color of light emitted by an atom, the energy, which gives me a frequency, which gives me a color. And it's always the same to a part in 10 to the 8th. All right? That's why a neon light always glows the same color. All right? Or if you've ever in a lab looked at a sodium lamp or something like that. And actually, interestingly, this enters into the atomic clocks. In atomic clocks, they manage to arrange an atomic state that has an anomalously long lifetime. And they basically excite it, they let it decay, and they measure the frequency of that decay. Because this is actually, that would be, there's 10 to the 7th seconds in a year. This would be, if I had a clock based on the frequency of light emitted by an atom, this would go wrong by 1/10 of a second in a year, which sounds pretty good. But in fact, for atomic clocks, they've found systems where the lifetime is more like a second, and delta E, or 1/10 of a second, delta E over E is 10 to the minus 15. Okay? Which is to say they lose a part in 10 to the 8th in a year. Okay? And they actually need that. Do you realize that the GPS system relies on atomic clocks? Because the timing accuracy, also taking into account general relativity, requires that sort of thing. So in fact, you wouldn't have GPS. GPS wouldn't function if I wasn't teaching this class. Not that me teaching this class caused GPS to this causality backwards, but right? Both general relativity and quantum mechanics, and this really spectacular application of quantum mechanics is needed for the basic technology of GPS. I was talking on the phone with a colleague this morning. He's been completely he's been made completely dependent now. He was in the car and his GPS had just gone out, and he needed to hang up because he wasn't able to find the airport if he. Now that he's been relying on GPS for the last 2 years. So it's all thanks to quantum mechanics. All right. But again, I want to just point out this is a basic feature of systems. If you want a system that has a precise energy, you look for something that's long-lived. If you have something that's very, very short-lived, and this applies to like particle physics, there's lots of particle physics reactions which either can be take a long time to play out, or can happen really, really, really rapidly. If they happen very, very, very rapidly, they have a very poorly defined energy. Okay? So this is a more tangible version of this than the one I told you before about, oh, the vacuum is full of particles that are created and borrow energy. I mean, that actually is true, but I mean, I know that seems like complete science fiction. This is really concrete. And the next time you use GPS, you'll be using that. All right. So I started the day with that's a bit of a detour, although an interesting one, I hope, and one you should know about. But let's just go back. We're trying to solve our particle in a box problem. But that's all I'm going to speak about in terms of I believe that's all I'm going to speak about this semester about the sort of time treatment in quantum mechanics. It's there, but it's for a more advanced class, except to just say the comments I've made so far. All right. So, having done that, remember how we separated the variables. We also have the equation minus h bar squared over 2m d squared psi dx squared. And because by psi I mean the only x-dependent part, I don't have to write the partial derivative anymore, plus u, the potential, which is a function of x, times psi of x. And that's just equal to E, the same E, the energy. This is the time-independent Schrödinger equation. And we can regard that as just your starting point, all right? From here on out, mostly on exams and homework and whatnot, you won't have to start with the full thing and write the time-dependent Schrödinger equation, because the time part is just so trivial, all right? I think I've probably assigned a homework where you have to work that out, but after you've done it, you've done it. You always jump to this, okay? And we're just going to solve that. Times psi of x. Wave function on all sides, okay? And again, so this is a wave equation. We solved it already with u equals 0, including the time dependence. But now we're going to solve it for this problem. And this problem, let's remind ourselves, the particle in the box, 0 to L, I'm drawing the potential energy here. It's infinity here. It's infinity here. Excuse me, it's 0 in the middle. These are regions 1, 2, 3. This is a little bit ugly. I'm going to have to write everything in terms of pieces mathematically, but you know, there's no way around it. So the way I'll write it is that u of x is 0 and 0 for x less than L. For x less than 0 and for x greater than L. And it's infinity out there. And it's 0 in the middle for x less than L and x greater than 0. Okay? That's just what I drew. Now, what do I do where the wave function is infinity? Okay? I'm sorry, where the potential energy is infinity. I have infinity here. I better put psi to 0 or I've got madness, right? I don't want to think about infinite energy. I don't want to think about trying to create a psi that has an infinite derivative, right? So out here, psi is 0 and psi is 0. I mean, look, let's just think physically. If I said the energy is infinite, I said I don't want the particle there. The potential energy is infinite, right? Just think classically, a potential, right, that's infinite, if I'm in a well, means that, you know, let's assume gravity is constant all the way up, and I'm in a well that's infinitely deep. I'm not getting out. Okay. So psi is 0 out here. And we're only worried about the middle. Okay, so it's really very simple. So in region 2, I simply have minus h bar squared over 2m d squared psi dx squared equals e psi. Right? U is 0 there. Very simple equation. And what are the solutions? Once again, I guess. And then I just make sure that my guess is right. Of course, it takes some practice to know where to put constants and whatnot. But clearly, I want something. I want to take two derivatives of it. I want to get the thing back. So my choices are essentially, well, okay, there is a little bit of practice you need. I mean, I have to know whether I want to use i's or not. But clearly I want to use exponentials or sines and cosines. Two derivatives means I can use sine or cosine, because if I do, you know, taking two derivatives, I'll get the thing back again. So my solutions are going to be like this. Right, just in general. You can imagine any of those will work. When I take two derivatives, I'm going to get a negative sign from these guys, which I need. Or if I take two derivatives and I have the I, I'll get a negative sign from squaring I. Everyone happy with that? Right? Okay? It turns out that for this problem, it's going to be useful to take sine kx. Okay? How do I know that? Well, practice a little bit, just experience. But what this is going to be determined by is what happens here and here at the boundaries. Mathematically, this is called a boundary value problem, which again, you'll learn to, you will take a math class where you sort of systematically learn how to solve these. And typically, what happens is that you pretty quickly learn what the solution is going to be. In this class, it's almost always going to be a sine or a cosine, or sometimes it's more e to the minus, and let me just use a different constant name, e to the minus or plus or minus alpha x with no I in it. Those are the types of things it's going to be. And then you're trying to find k, or you're trying to find alpha. And you're going to find it by figuring out what psi is at 0 and at L, because there's nothing in the middle to distinguish. Okay, so that's the work we're going to do. Okay, so what do I want to do at the boundary? And let me just tell you, I'm going to choose here psi of x equals a sine kx. I'm just going to, out of habit, pick k. This may no longer be a traveling wave. K may not have this, well, it will roughly have the same meaning as before, but let's just pretend it's a constant, and that's some constant. I don't know them, okay? I'm just going to choose this. If I choose wrong, the algebra will get hairy, and effectively I'll get back to my correct choice. Because if you add and subtract various sines and cosines, and you can get to the exponential or vice versa. So there's, in some sense, there's not a wrong choice. There's just inconvenient and dumb choices that just cause more work, but ultimately you get back to the same place. Like if you are, in general, you might choose a sine kx plus b cos a times sine kx plus b times cosine kx, and you say, I don't know if it's a sine or a cosine, okay? And then you'll find, and in this problem, it'll turn out the b is 0. Or I should choose e to the ikx, and I'm sorry, I should have put a plus or minus there. A times e to the ikx plus b times e to the minus ikx. And I'll start wiggling around, and it turns out in this problem, I'll find out that the one coefficient is 1/2, and the other a times, and the other coefficient is minus 1/2. And that amounts, with an I in front, and that amounts to sine. Okay? Are you guys following me? I'm talking a lot. For now, we'll take this and go, all right? But I need a rule to apply at the boundary, at 0 and an L. Okay, so now I got to think a little. All right. So at the boundary, I know that psi is 0 outside because it's infinite energy out there. So what am I going to do at 0 and L? And let me just look in a general way. Suppose I had a situation where at some boundary in x, we're just looking at the left boundary, say, and here psi is 0. And let's suppose here I have some psi of x. I don't care what it is. Let me just draw it as something that's not 0, right? So there's a jump there. I'm going to argue that you can't tolerate this. Okay, why can't I tolerate this? Let's think about the momentum, p. What did I say momentum is going to be? I somehow said momentum times psi, and maybe today or maybe by Friday I'm going to explain more what I really meant by saying the momentum is this. But for now, remember that I said the momentum times psi is h bar over I d by dx. Here, let me write it as a full derivative, because psi only depends on x, of psi. Okay? And let's go carefully. Remember what the definition of a derivative is. I'm going to take the limit as delta x goes to 0 of psi of x plus delta x minus psi of x over delta x. Okay? And if I take x to be right at 0, or actually just a little bit to the left of 0, okay? I'm going to take x to be, I don't know if you're used to the language, 0 minus. So at 0, but just to the left of it, right? Okay? Then, and let me come over here, then P times psi is going to equal h bar over I psi at x, which is 0, plus delta x, minus psi at x just to the left, which is 0. Oh, and I want to write the limit. I'm sorry, I want to write the limit there. P at psi equals the limit as delta x goes to 0, divided by delta x. Okay? Now, as delta x goes to 0, I'm going very slowly here to show something which I really could have just argued. But I'm just trying to be very explicit about it. As delta x goes to 0, I was on the right side and I came down to 0 and I just simply said, I said one thing. I just said, look, let's assume psi here at 0 is not 0. It's bigger than 0. All right? It's just some number and it's bigger than 0. I don't really care what else it's doing. The answer is then that P is this thing here. It's this finite term divided by delta x as delta x goes to 0. This is infinity. Okay? Now you probably, I'm just rehashing the argument you learned in calculus, but maybe you've forgotten. That's why I rehashed it carefully. That if I have something that has an abrupt step, its derivative is infinite. Okay? So really all I'm saying is if the momentum is somehow the derivative of the thing, and the thing has an abrupt step, the momentum is infinite. And that's not good. I don't want the momentum to be infinite at 0 or at L. Okay? So I then therefore require I'm going to require psi equals 0 at 0 and L are equal to x, right? At the boundaries. So my boundary value problem is simple. I want the psi to be 0 at the boundaries. We're going to do some problems where it's not quite that. It's a little different than that. Okay? So let me erase this. And an argument like this has gone through in the book. You're going to have to learn to apply a couple of different arguments about the boundaries, and that's it in this class. Okay? Basically, we're going to have to think about the first derivative and the second. That's it. And it's pretty straightforward. And then you got to just remember that, how that argument went. All right, so psi, I'm going to call it psi of 2 because it's in region 2. At 0 equals 0 equals a sine k times 0. And now you see why I chose sine and not cosine, right? That is 0. So this works out. I mean, perhaps I did you a disservice if I had tried psi of 2 equals a sine kx plus b cosine kx, just as I said, and I plug in 0, then that would be, psi of 0 would be b, and then it's equal to 0, so b equals 0, right? So that's all that would have happened if I taken the more general answer. Okay, so it's 0. Psi at L also equals 0, equals a times sine times k times L. Okay? What does that imply? That implies that k times L, how do I make the sign of something 0? It's non-zero at pi over 2, 3 pi over 2, etc. It's 0 at 0, 2 pi, 0, 4 pi, etc., going around the circle. It's 0 at n pi, where n is 1, 2, 3, dot, 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 dot. Okay? So I've learned something. If I will, I could say k sub n equals pi over L times n. N equals 1, 2, 3, dot, dot, dot. I'm embarrassed. I forgot to, well, it's fine. I'll do this now. I should have done it earlier. Having chosen this solution, I have done the right thing. I have examined the boundary value, and I have found something about k. I probably first should have done something else, which is I should have plugged this into this equation and seen what, first off, does it work, which I think it will, and two, what does that tell me? So apologies. Let me do that now. Sort of working it backwards. In general, you guess an answer, you plug the answer into the differential equation, you find out if it's a solution, and typically you learn one of your constants at that point. Then you apply your boundary values, and you learn whatever other constants there are. Okay? Plugging this in, minus h bar squared over 2m d squared by dx squared of a sine kx, and I'll just leave it as k for the moment, equals e a sine kx. Okay, two derivatives of that. Okay, a isn't affected by the derivatives. Taking the derivative of sine, I get minus k cosine. I get k times cosine. Taking the derivative again, I get another factor of k. But the derivative of cosine has a negative sign. Okay? Okay? And sine cancels out, a cancels out. Okay? And not surprisingly, I get h bar squared k squared over 2m equals e. I had this before when I had a free particle. Not surprising, this is a free particle. This is the solution to a particle with no potential, at least in the center, so I should get the same result, and I do. So if you will, k can be solved. It's 2me over h bar with a square root there. Either I write it k equals this, or I can write e in terms of k. All right? So k is related to e. It is like the momentum. H bar times k is like the momentum. But we're going to be careful here. This is not exactly the momentum, okay? And I'll show you what that means in a minute. Okay, so for now, though, this is like one fundamental thing I learned. And I learned that from just how that solution plugs into the wave equation. And then the boundary value told me this. It told me k, I can't have any old arbitrary k. I have to only have these values of k. And so what I want to do is, I'll do it here. Let me just combine those two facts. E sub n, and I'm going to write sub n because e depends on k. It's h bar squared over 2m times k squared. So that's h bar squared pi squared over 2m L squared times n squared. And n is 1, 2, 3. That's my basic thing. That's what I was after. Dot, 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 dot. And just for completeness, let me rewrite down n pi over L. Now I'm plugging in the value of x that I learned. All right? Okay. I have a number of things to say about this. One thing to say is, well, let's learn what A is, okay? I'm going to talk about the energy. I'm going to talk about where the particle is, what its momentum is, but first let's find A, okay? You guys have any idea how I might do that? Any idea? What? Yeah. Find the answer at L over 2. Well, that was interesting. You're saying find the energy at L over 2. You're thinking classically, okay? I don't want to be mean, but harsh on you. But what is psi going to give us again? What is psi going to help us with? What is it? It's going to be probability. What do I have for a well-behaved probability? You guys, I've said it a couple of times, but I just said it subtly. So probability has to be 1 when integrated over, right? In other words, I have one particle in this box, okay? The statement that I have one particle in this box is the statement that the probability that it's anywhere is 1. I want the probability, what I want is 1 to equal the integral over the probability over all space. All right? Where in general it's going to be that. And I'm throwing away the time part because I've already shown that the time part goes away when I do this. All right? Now, less than 0 and greater than L, psi is 0, so my integral only goes 0 to L. And it's just, its psi is this bit, a squared times sine, a squared sine squared n pi over L times x dx. Okay? I need to solve that integral. Let me erase this. This is taking up a lot of room. Here's a little bit of math. I'm sorry I'm going to drag you through it, but this is like eating your Wheaties. It's good for you. You have to do this. You have to be, I'm going to show you some math. You got to be able to do this. Okay? Oops, I didn't square it. Got to be able to do that. That's psi squared, or psi star psi. There's a couple of trig identities that are very useful. Sine squared of A is 1/2 of 1 minus cosine of 2A. In some sense, you ought to commit that to memory. There's also a similar one that will come up a lot. You really have to commit these to memory. Actually, I don't commit those to memory. I commit cosine A plus B equals cosec sine B plus sine A cos B, and the same thing for sine. I commit those to memory and rederive these when I need them. But or you can just always look them up. But you got to be able to get that at the tip of your your fingertips. Okay. So let me apply that here, because look, I'm going to integrate sine, and I don't like to integrate sine squared. So 1 equals a squared comes out of the integral. 0 to L, and I rewrite sine squared as 1/2 of 1 minus cosine 2 times the thing inside the integral, inside of the sinusoid dx, right? That's just using this top equation. You may be able to look ahead and realize that the integral of this cosine with 2 pi times an integer is always going to be 0, whether this was cosine or sine, in fact, because it'll be the same at 0 and L when I plug in. But let's just go through it, okay? This term is going to vanish, but let me just go ahead and prove that. So it's a squared. Okay, so this is the integral of a 1 times dx. So the integral of this 1 is just x. There's a half out front. So I have x evaluated at 0 and L. Minus, sorry, I can integrate this directly. The integral of cosine is sine, and the prefactor of x comes out and is in the denominator, so L over 2 pi, 2n pi, The integral of cosine is sine. There's no negative sign involved. And I'm evaluating this from 0 to L. And then all of this is inside of brackets here with a squared over 2 out front. This is just L. This is sine of L cancels the denominator, so that's 2n pi. That's 0 and minus 0. That term is 0. And even if this were cosine, it's the same here and here, so it would have been 0. Anyway, so that term's gone. And so this is just 1 equals a over 2l, a squared. And therefore, a is the square root of 2 over l. I needed to do this. And we're going to be doing this type of calculation several times here. So that's part of solving these quantum mechanical problems, is finding all the constants. So now finally that is complete. No unknown constants. Okay? All right. Okay, let's talk about this a little bit. Let me draw something here. So this is interesting. I put the particle in a box, and what happened to the particle is it can't have just one energy. Or sorry, I said that wrong. It can't have any old energy. It can only have energies with this formula where n is a number, an integer. All right? This finally is why it's called quantum mechanics. Okay? Quanta meaning, quanta, like a single, like a quantized means broken into discrete numbers. There's discrete energies for various values of n. A nice way to represent this situation is I'm going to draw this kind of a funny drawing where I'm going to combine two things at once. Here on the left side, I'm going to write the energy of the thing. And this will be E1 for the n equals 1 state, where E1 would have been just simply h bar, this stuff with n equals 1. Okay? Let me also combine on this drawing a drawing of psi going from 0 to L, and it's just that. Incidentally, I could have chosen a negative sign here for my coefficient, and it wouldn't have made a darn bit of difference. There's no meaning to the sign of the wave function, because I always square it. Okay? Then, if n equals 2, well, let me actually be a little more careful. The energy is 4 times higher. So this, 1, 2, 3, 4. It's right there. And it's sine of, oh, and sorry, when I sketched that in, I sketched it quickly, right? But what did I do? If for n equals 1, this was sine pi L over x. Sorry, and I did go quick. It started at 0, and I went to L, and I went through L over 2, and so that just went up to a maximum and back down to 0. But now if I put a 2 there, okay, if you think about it a second, I start at 0, I go out to L. This thing is running from 0 to, L's cancel and a 2 there. I'm running from 0 to 2 pi, okay? Which is to say I went all the way up. I'm sorry, I want to start at the same height. I went all the way up, I come down, and I come back. So this is the n equals 2 solution, right? And that's what psi looks like. Then n equals 3, and this was 4E1. Then at n equals 3, I have 9 times E1, because n squared. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's up there a ways. Let me just break my scale and sketched it in right here. E3 equals 9E1. And by the way, does this kind of look like atomic states for those, that you may have learned in chemistry class? It's rooted in the same mathematics. N equals 3. 3 pi over L. So by the time I plug in x equals L, I've gone from sine of being 0 to sine being 3 pi. Okay, so that's 1.5 complete cycles. So that's something that 1 cycle means I went through 0 once. 2 cycles, 1.5 cycles means I go through 0 twice. Okay, it's the next thing I can squeeze in and hit 0 on both ends. Okay, so there was a whole cycle and then a half. All right? And so that's the behavior of the system. I'm allowed these certain energies, and I'm allowed, that's what the wave function looks like. And okay, let me just spend 15 more seconds to sketch out. That's what the wave function looks like. What does the probability look like? Let me go ahead and erase this where I wrote what those energies are. If I just tried to sketch the probability of x, it's the square of this thing, okay? And I learned about the square, well, one way to talk about it is I learned about the square of the thing. It's 1/2 of 1 minus the thing itself with twice the frequency, if you will. And what that looks like, this one, instead of kind of coming down in a cuspy way, it looks like that. It's part of a doubly fast oscillation that happened to hit 0 here. This one's similar, but this negative part goes up, but instead of looking like that, instead looks like that, okay? And similarly, like that. So that's what the probability looks like. I'm sorry I'm running over, but so the point is now, the particle actually literally, if it's the n equals 3 state, it can't be here or here. If it's the n equals 2 state, it can't be in the center. Okay, so there's these interesting features about what the particle's doing that have no classical analog. If I stick a quantum mechanical particle in a box, it has this weird property that it decides to live in these certain states that aren't uniform, they're not smeared out in there, and they have these only very specific energies that are allowed to it. Okay? And so much of a basic chemistry and atomic physics is kind of based on these ideas, these energy levels that are allowed. Okay. Sorry I went over. I'll try not to do that again.